Okay, so this is actually the 2010 mechanics test. It's actually taken from past papers. I'm not quite sure which past papers it was, but we'll go through this. So the first question here in the multiple choice, the graph shows the variation with time of the acceleration a of an object. So you've got your acceleration here and you've got your time here. The object is at rest at time t is equal to 0. Which of the following is the velocity of the object? Now usually we're looking at two things. We're either looking at the slope or the gradient. Now the slope is always your change in your y over your change in your x. A change in vertical, change in horizontal. In this case our acceleration is our vertical. So it's good just to look at your units which come out. So we would get meters per second to the -2. And we would be dividing by your horizontal, which is time, second. You'd actually get a meters per second to the -3, so a rate of change of acceleration, not velocity. The second thing is that we look at area. Now when we look at area, we look at multiplying these two values together. So we would multiply that times that. So that would be meters per second to the -2 times by a second, which gives you a meters per second, which indeed is velocity. So we're going to need to find the area in this case. So I'm going up to 6 seconds. So it's over here down to 6 seconds. If I go across here, I'm at 12. So this is actually going up to 12. So I'm actually going to find the area of this region here. And because it's a triangle, we use half the base. The base is obviously 6 times the height there, which is 12. And that works out to be half of 6 is 3 times 12 is 36. So 36 is the correct answer for that one. Okay, so let's go on to the next question. Let's pull it down here. Alright, so we've got this one over here. We've got an object is dropped from rest from a point several hundred meters above the surface of the earth at time t is equal to 0. So it's dropped. So it starts off with an initial velocity of 0, wouldn't it? And the object strikes the ground, t is equal to t, and the air resistance is not negligible. So we have which of the following sketch graphs best shows you look into best, not actually maybe the actual variation with time t of the speed v of the object. So when looking at them, we need to start at 0, and all of them all start at 0 like this. But you've got here, because you're going to get a terminal velocity at some point, it would need to increase at a constant velocity, but then decrease. The increase in the velocity is going to decrease, and it's going to plateau out. So actually C would be obviously the best one. I mean, this one over here, there is just a constant increase. That would be no air friction. Here we're starting off at extremely high acceleration, which wouldn't work. Here you're getting the sudden change, which wouldn't work. So this certainly is the best. The only problem with this is that at time t, where you'd expect the velocity to be 0, it's all going to 0, it continues. So that's a little bit strange. But definitely C would be your correct answer for that. Alright, so that's question 2. Going on to question 3. Let's take it down here. Alright, this is pretty straightforward. Which of the following is a correct definition for average acceleration? It would be A, change in velocity over change in time. I mean, the next best would be your change in speed, but generally acceleration is taken as a vector, and so we'd be looking at the vector quantity. Acceleration can be a change in direction of the velocity, not necessarily a change just in magnitude, as C would be. So A is your correct answer for that one. Going down here, question 4. Alright, so we've got this one. A picture frame is supported vertically by a wire that is looped over a light peg. Sorry, I can't read this very well. Over a horizontal light peg P. There is no friction between the wire and the peg. Alright, so it's supported vertically there. You would think it would be stationary. The mass of the picture is uniformly distributed, and Px is equal to Py. Which of the following best represents the free body diagram of the forces acting on the peg? So we got this over here. Now we can imagine the forces. Obviously there would be a force in that direction, the tension in that wire, and there would be a force in that direction. And because this picture hopefully is standing still, it's not accelerating anywhere, all the forces acting on that would cancel each other out. The resultant force would be zero. So there must be a force going up there that would cancel out these two forces over here. So looking at that, we would definitely think that B would be the correct one. This over here, because we would look at this, it looks, I mean, D is reasonably possible, but these are all equal, and this seems to be a 90-degree angle here. If this angle is 120 degrees, then you would have all the sides the same. So, but they're not. This looks like 90 degrees. So if I construct a parallelogram from there, that length there should equal that length over there, and it seems to. Alright, so we'll take B as being the correct answer in that case for question 4. Important thing there to realize, no acceleration, therefore all the forces are cancelling each other out. There's no net force acting. Going on to question 5, we have all objects at a particular point on the Earth's surface have the same value of free fall acceleration. The reason for this is because, now I'm going to need to do a little bit of explanation here. We usually do this a bit later in the curriculum, but we define mass in two different ways. We define it by Newton's second law, that force is equal to mass times acceleration. So I can calculate the mass of any object by applying an unbalanced force on it, dividing it by the acceleration that it produces, and it will give me the mass. And we call this the inertial mass. I can also define mass in terms of the force due to gravity. So if I've got any object, and let's just use the Earth and any other object, they are related by this formula. I can, if I get two objects and I can find the force if I know the distance between, sorry, this is an r squared value there. This is an r squared value. If I find the distance between their centers and I divided it, I can actually calculate the mass by means of that formula. And this is known as the gravitational mass. Now, if I have an object and it's been attracted by the Earth, then it will experience a force due to gravity, which would equal to big G, mass of the Earth, mass of the object divided by basically the radius of the Earth squared. Now this force over here is actually equal to ma by Newton's second law, and this over here, if I calculated this mass in terms of this way, this will be according to Newton's second law. This mass over here is due to the gravitational mass, and I can cancel these two out because they work out to be the same, and therefore the acceleration is equal to big G me over r squared. Now, as you can see, the acceleration is independent of the mass of the object, and we call this a here, we give that the symbol g, and that is your 9.81, or as we often use, 10 meters per second. Okay, so it's because the gravitational inertial mass of each object is the same. That's the reason why we have it. Alright, if you need further help on that, I'll be glad, and I will discuss this later on in the course.